Okay, I wanted to finish up section 11.6. We are talking about inverse functions. Now, the inverse of a function is just simply where you're switching x and y. We talked about the term one-to-one. One-to-one just means that the inverse is a function. Okay, and then we also looked at the horizontal line test, which can be helpful in determining if the graph of a function is one-to-one. Okay, now we use the notation that you see here. We read this as f inverse of x, and we use that to represent the inverse of a function f of x. Okay, be careful with this notation though. If f is not one-to-one, then we should not use the inverse function notation. This is because the inverse is not a function. Okay. Also, f inverse is just a symbol for representing the inverse of a function f. The negative one is not an exponent. So, f inverse does not mean the reciprocal of f. If I had f of x to the negative 1 power, which I don't, okay, I have f inverse of x, but if I had f of x equal to the negative 1 power, that would be the same as 1 over f of x. F inverse of x is not the same as 1 over f of x. Okay, so when we compute an inverse, we don't just write 1 over that function. Okay. Let's take a look at this one here. Two one-to-one functions, f of x and g of x, are inverses of each other if f composed g of x is x and g composed f of x is x. The way to check if two functions are inverses of each other is through function composition. So let's take a look at problem 44. Determine if the functions are inverses of each other. Part A, okay, we've got f of x equal 2x plus 3, and then g of x equal 1/2 the quantity x minus 3. Well, in order to check that, I need to check that f composed g is x and g composed f is x. Let me do that. F composed g of x means that I got to plug g into f. G is 1/2 the quantity x minus 3. So everywhere that I see an x in f, there's only 1. I need to replace that with 1/2 the quantity x minus 3. And that's what I'm doing here. Okay. Now I'd want to simplify. 2 times 1/2 is 1. And then you got x minus 3 plus 3. Okay, negative 3 plus 3 is 0. And so I get just x then. Now I also want to check that g composed f of x is just x. Well, g of f of x means that I need to plug f into g. F of x is 2x plus 3, so everywhere that I see an x in g, there's only 1. I need to replace that with 2x plus 3. And I've done that here. Replace x with 2x plus 3, and then I need to simplify. Okay, well, 3 minus 3 is 0, right? And so then that leaves me with 1/2 times 2x, the 2's cancel, and I get just x. So because both of these calculations ended up being just x, that is a verification saying that, yeah, these two functions are inverses of each other. Now, earlier I was talking about the inverse function notation. I could use that here if I wanted to. Instead of calling this g of x, I could call this f inverse of x. That would be okay. Part B, okay, f of x equal 6x minus 10, and then g of x equal 1/6 x plus 10. Are those inverses of each other? Well, let's check. So I got to plug each function into the other and check and see that I get plain old x. Let me do that. So f of g of x means I got to plug g into f. G of x is 1/6 x plus 10. Plug that into f. Okay, there's only one x in f. So I got to replace that with 1/6 x plus 10 and then simplify. When you distribute 6 times 1/6 x is x, and then 6 times 10 is 60. X plus 60 minus 10 would be x plus 50. Okay, so I don't get just x. I get x plus 50. I don't even need to bother checking the other side of this because I didn't get just x. At this point, I can conclude that no, these two functions are not inverses of each other. Now, by the way, just an observation here, to make them inverses, we would need parentheses around the x plus 10. We don't have that, okay, but we have the parentheses up here in this problem. The point of that observation would be to say, like any other math problem, the parentheses do matter, okay, and when they're not written, the conclusion is different. So we see that here. All right, let's take a look at this one next, the next page. The domain of a function f of x is equal to the range of the inverse of the function. Also, the range of a function f of x is the same as the domain of the inverse. Okay, that can be helpful in determining domain and range. We'll use that here later. Problem 45. Let's take a look at that. The graph of a function f is given. That's the curve in black. Graph the inverse of f, and then state the domain and the range. Well, inverse is all about switching x and y. So with this graph here, I'm going to switch the coordinates and plot the new points. Let me do that. Okay, so here's -4, -2. That's now going to be at -2, -4. Here's -2, 0. That's going to be at 0, -2. And then here's 3, 1. That's going to be at 1, 3. And then I can connect these points with two lines. And that curve that I drew in red then would be my answer. That would be the inverse. Now, notice how f is 1 to 1. They didn't ask that, but I could know that right away, that f was 1 to 1, because f passed the horizontal line test. So the inverse is a function. Remember, 1 to 1 just means that the inverse is a function, which means that I could use the inverse function notation if I wanted to. Okay. I've also drawn the line y equal x. I did that on purpose. It says in this note here, notice that the graph of the inverse is a reflection across the line y equal x. This will always happen when you graph a function and its inverse on the same picture like we've done. They will always be symmetric to the line y equal x. So one way to look at how we got the graph of the inverse is we started with the graph of f and we rotated that about this diagonal line here. Okay, let's also state the domain and the range of f. F is the curve in black. Domain means we're talking about x. So it looks like if x is between -4 and 3, and you look above or below those values, you're going to be somewhere on this graph here that is in black. So the domain -4 to 3. How about the range of f? Or range means I'm talking about y. Well, if I'm between -2 and 1, including those numbers, and I look to the left or to the right, I'll be on the curve in black. Okay, so the range would be the interval -2 to 1. Now, the range of a function is the same as the domain of the inverse. So another way that I could have got this set is I could have looked at the inverse, that's the curve in red, and I could have stated its domain. Okay, so let's do that just to check that the numbers would be the same here. The inverse is the curve in red. Domain means I'm talking about x. So the conditions on x for the curve in red are such that if you're between -2 and 1 and you look above or below those values, you're going to be somewhere on the curve that is in red. But that's the same interval that I've already got written here, right? The range of a function is the same as the domain of the inverse. By the way, we'll need to just make a mental note of that. When we get into the topic of logarithms in the next chapter, I'm going to be talking about this problem again, actually. All right, let's take a look at problem 46. We want to find the inverse of f and then state the domain and the range of f. Part A, f of x equal 2x plus 3. Let's find the inverse of f. Y and f of x mean the same thing. And so I'm going to first rewrite this equation in terms of y and x. And then remember, with an inverse, it's all about switching x and y. So that's what I've done next. I've switched x and y. And now if I solve this new equation for y, I'll have the inverse. Let's do that now. So I'll need to subtract 3 and then divide by 2. And I'm looking at y equals 1/2 the quantity x minus 3. I could use the inverse function notation, and I could say f inverse of x equals 1/2 the quantity x minus 3. That'd be my answer. Okay, now I can go ahead and circle that. We have already verified that this is the correct answer from problem 44a. So if I go back to problem 44a, notice how f of x is equal to 2x plus 3. Okay, that's the same function that I gave you here. Now in problem 44a, I just told you the inverse. I didn't say where this was coming from or anything. I just, here's a function. Let's verify that these are inverses of each other. And so we've done that, right? Yes, these are functions or inverses of each other. So I know that this is the correct answer. I guess this would be a rare time where I've actually checked my answer before I've computed the answer type thing. But of course, you'll always know if two functions are inverses of each other by plugging each one into the other and checking that you get plain old x. Okay. State the domain and the range of the function. Okay, so f of x is a linear function. The domain of any linear function is all real numbers. How about the range of the function? Well, the range of a function is the same as the domain of the inverse. Let me use that here. I've computed the inverse. The inverse is also a linear function. Remember, a linear function is a function of the form y equal mx plus b. If I distribute the 1/2, I get y equal 1/2 x minus 3/2. That's y equal mx plus b, right? And the domain of any linear function is all real numbers. Therefore, the range of f of x would be that same set. It's going to be all real numbers. Okay, let's try part B. Here's f of x equal negative x squared plus 2. Find the inverse. Well, let me first rewrite this in terms of y. I got y equal negative x squared plus 2. No harm with that, right? Y and f of x mean the same thing. And I want to find the inverse, so it's all about switching x and y. If I switch x and y in this equation, I'll have x equal negative y squared plus 2. Now I would need to solve for y. And so let me do that now. I'm going to add y squared to both sides and then subtract x from both sides. To get y all alone, I'm going to then take the square root of both sides. And of course, don't forget about the plus or minus when you do that. Okay. Y is equal to plus or minus the square root of 2 minus x. That would be the inverse of the function. Okay, and so I could circle that answer. Now, before I state the domain and the range, there's a note here. F is not 1-to-1, since there is no inverse function. You see, I wouldn't want to use the inverse function notation like I was doing over here in this problem in part B, because I don't have a function. We know that with a function to occur, for each x there's only one y. There can't be a plus y and a minus y, right? There's only one y. And we don't see that happening here. So I wouldn't want to use the inverse function notation. Okay, if I did that, it's like I kind of missed the idea that f is not 1-to-1. So the point is, don't use function notation if you don't have a function. It is totally fine to just leave your answer in terms of x and y. Of course, you'll want to do that if you don't have a function. Let's state the domain and the range of f. Okay, so f is a quadratic function. We did things with quadratics quite a bit, and the domain of any quadratic is all real numbers. Okay, like I could square any number, multiply by -1, and then add 2. I could do that to any number I want, right? And the range of the function, okay, there's a couple of different ways that I can get the range here. One option is to state the domain of the inverse. I've computed the inverse. What is its domain? Well, I know that I don't want an overall negative to be underneath the square root sign. I'm not doing anything with I or imaginary numbers. So I could set 2 minus x to be greater than or equal to 0, since I don't want that to be a negative, and add x to both sides. It looks like anything that is 2 or less is going to be okay to use, and so that would be the domain of the inverse, which is also going to be the same set of numbers as the range of the original function. Now, another way that I could see this is, remember with a quadratic, you are working with a parabola. This parabola would be opening down because of the negative that's in front of the x squared term, so opening down. The plus 2 means that I would just take y equal x squared and flip the graph upside down, as I said, but then shift up 2 units. Okay, so the vertex would be located at 0, 2. Anywhere that's 2 or less than on the y-axis would be represented in the range. Okay, that'd be the conditions on y. Part C is the last one here. We've got f of x equal 1 over x plus 2. Let's find the inverse of f, the domain of f, and the range of f. Okay. So I'm going to first rewrite this in terms of y, and then switch x and y, and then begin solving for y. Multiply both sides by y plus 2. That'll get rid of the fraction that's there on the right. Distribute x, and okay, if I subtract 2x and then divide by x, y would be all alone. Now, I can use inverse function notation here. That'd be fine. I didn't have any plus minus thing come up like in the last problem, so I could call this f inverse if I wanted to. F inverse of x equals 1 minus 2x all over x. That would be my answer. And I could check that if I wanted to. You know, you can always check by plugging each function into the other and verifying that you get plain old x. So that's what I've done here on the side. Okay. By the way, a problem like this would be good practice with fractions. So let's find f of f inverse of x. Here's what I think f inverse is, what I've computed. So let me, everywhere I see an x and f, I'm going to replace that with 1 minus 2x over x. There's only one x to replace in f. And now you got to simplify. Okay, does this expression here end up being just x? That's the next question. Well, 2 is the same as 2 over 1. So if you multiply the top and bottom by x, 2 is the same as 2x over x. And now I've got my common denominator there down under, so I can keep x and then add the numerators. 1 minus 2x plus 2x is 1. The negative 2x plus 2x is, you know, those are gone. 1 divided by 1 over x, if you flip the denominator, that'll give you just x. Now at this point, I'm feeling pretty sure that I got the right answer. Okay, but you know, to finish the check procedure, I am going to also verify that f inverse of f of x gives me just x. Now f of x was given to us, that's 1 over x plus 2. So everywhere that I see an x in the inverse function, there's only there are 2 of them, I need to replace those 2 x's with 1 over x plus 2. And so I've done that. Okay, and now I got to begin simplifying. So the question next is, does this guy here become just x? Well, 1 is the same as x plus 2 over x plus 2. And that's how I'd want to think of this, because now I've got my common denominator up top. And I can combine these fractions to a single fraction up top. I'm going to keep the x plus 2 and then add the numerators. X plus 2 minus 2, the 2's are gone. That'll give you x. X over x plus 2 divided by 1 over x plus 2. You're going to flip the denominator there on the next step. X over x plus 2 times x plus 2 over 1. The x plus 2's cancel, leaving you with x over 1, which is just x. Okay, so because both of these composite functions gave me just x, that tells me that indeed I do have the right answer there, and I can circle that. Okay, and suppose that we wanted to know the domain and the range of f. Well, here's f of x. Of course, I can't divide by 0, right? So I wouldn't want x to be negative 2. That's going to be a problem. Okay, I can use any other number I want, just don't use negative 2 because I know I can't divide by 0. How about the range of the function? So the range of a function is the same as the domain of the inverse. Okay, what's the domain of what I have circled here? Well, again, I know I can't divide by 0. X is all alone in the denominator, so just don't let x be 0. All real numbers except 0. Well, that's going to be the same set as the range of the function then. All real numbers except 0. All right, that's it for the section. So the homework is on page 926. Be sure to look at the problems there, and we're now done with chapter 11.